Something very strange is happening in the early universe. And scientists have no clue why their theories are failing to explain these strange mysteries. Scientists are finding thousands of strange objects in deep field images and they have no idea what exactly they are looking at. Recently, astronomers have discovered many strange objects in the early universe and they said that these are not galaxies because these objects are completely different compared to early galaxies. James Webb Space Telescope just detected another universe. The announcement sent ripples through the global scientific community as researchers pored over the data streaming in from the telescope's most sensitive instruments. Early observations revealed faint patterns of radiation that did not conform to any known cosmic structures within our own universe. Instead, these patterns hinted at a region beyond the cosmic microwave background, as if the telescope's gaze had pierced the veil of our universe's edge. For decades, cosmologists had debated the possibility of a multiverse, an ensemble of universes each with its own laws of physics. But tangible evidence remained elusive. Now, with Webb's unparalleled resolution and infrared sensitivity, a tantalizing glimpse of something truly otherworldly had emerged. Before we start, smash the like and subscribe buttons for more updates. The detection began during routine analysis of deep field images, where astronomers seek to push the observable horizon ever farther back in time. Unexpectedly, a diffuse glow appeared just beyond the furthest reaches of the observable cosmos. At first glance, it resembled the ghostly afterglow of a primordial galaxy. Yet its spectral fingerprint was entirely unfamiliar. The infrared wavelengths captured by Webb's near-infrared camera and the mid-infrared instrument showed temperature fluctuations and polarization patterns inconsistent with the cosmic microwave background. Follow-up observations confirmed the signal's persistence. It was neither an artifact of instrumental noise nor a quirk of data processing. Webb had quite possibly glimpsed another universe. As the news spread, theoretical physicists worldwide scrambled to interpret the findings. Some proposed that the signal constituted gravitational leakage from a parallel universe, ripples traveling through higher dimensional space and leaking into our own. Others suggested that what Webb had captured were echoes of a cosmic collision, a moment when two bubble universes brushed against each other in the vast multiversal expanse. According to models of eternal inflation, our universe is one of countless bubbles inflating and expanding, occasionally colliding at their boundaries. If such a collision had occurred in the distant past, its signature might still linger as faint distortions in the cosmic microwave background, detectable only with the sensitivity of Webb. The implications of confirming another universe reached far beyond academic curiosity. Philosophers, theologians, and artists alike grappled with the profound questions raised by the existence of a multiverse. If our universe were but one bubble in an infinite foam, what would that say about the uniqueness of our cosmic story? Would the laws of physics be identical in these adjacent bubbles, or would each universe harbor its own constants, forces, and particles? The discovery forced a re-examination of long-held assumptions about the nature of reality, inspiring a renaissance of interdisciplinary dialogue that bridged the sciences and humanities. In the days following the initial detection, teams around the world mobilized to verify and extend Webb's observations. Ground-based observatories equipped with radio and sub-millimeter antennas trained their instruments on the same sky region, searching for corroborating signals. Meanwhile, theoretical workshops convened via virtual platforms where experts in quantum gravity, string theory, and cosmology debated the signal's origin. Some cautioned against premature conclusions, noting that unknown astrophysical processes could mimic the observed features. Others countered that Webb's data offered a clear window into phenomena that standard cosmology could not explain. The tension between skepticism and excitement fueled a dynamic scientific discourse that played out across academic journals and conference calls. One of the most compelling interpretations involved the concept of gravitational waves emanating from the boundary between universes. In this picture, the collision of two bubble universes would generate gravitational ripples propagating through the fabric of the multiverse. When such ripples enter our universe, they could manifest as minute distortions in the cosmic microwave background and as anomalous infrared signals, precisely what Webb detected. If this scenario held true, it would provide the first direct evidence of higher dimensional spaces and lend support to theories that posit extra spatial dimensions beyond the familiar three. At the heart of the debate lay the challenge of distinguishing between exotic multiversal phenomena and more conventional explanations. For example, some researchers pointed to faint emissions from intergalactic dust heated by the first generation of stars as a potential source of the infrared glow. Others examined the possibility of gravitational lensing by dark matter concentrations at the edge of the observable universe. Yet as successive rounds of data refinement eliminated many of these mundane scenarios, the case for a genuinely novel signal grew stronger. Each new analysis tightened the constraints, gradually tipping the balance toward the extraordinary conclusion that Webb had in fact glimpsed another universe. The ripple effect extended beyond the scientific realm into popular culture, where the public's imagination was captivated by the notion of parallel worlds. Social media platforms buzzed with speculation, fan art, and science fiction narratives inspired by the discovery. Filmmakers and authors found fresh fodder for stories exploring the consequences of contact between universes, conjuring scenarios ranging from peaceful exchanges of knowledge to cosmic cataclysms. Educators seized the moment to engage students with hands-on projects simulating bubble collisions and multiverse dynamics, sparking curiosity about the frontiers of cosmology. Back in the laboratories, instrument teams worked tirelessly to push Webb's capabilities to their limits. By adjusting exposure times, filter configurations, and calibration procedures, they aimed to extract every ounce of information from the faint signal. Simultaneously, proposals for new observational campaigns grew in number and ambition. Space agencies began discussing potential follow-up missions specifically designed to probe multiversal boundaries, featuring ultrasensitive detectors and novel measurement techniques. The concept of a dedicated multiverse explorer mission, once a fringe idea, now garnered serious consideration in strategic planning documents. Beyond the technical challenges, the detection raised deep philosophical questions about the nature of scientific evidence. Historically, cosmology has relied on observations within our own universe, using the cosmic microwave background, galaxy surveys, and supernova measurements to build models. The notion of inferring the existence of other universes pushed the boundaries of empirical science, compelling researchers to refine criteria for what constitutes valid evidence. Debates emerged about the role of falsifiability, the interpretation of Bayesian probabilities in a multiverse context, and the weight of indirect signals in scientific inference. The discourse illuminated the evolving landscape of scientific methodology in the age of grand cosmological discoveries. The story of Webb's detection also highlighted the importance of international collaboration. Scientists from dozens of countries contributed to the effort, pooling expertise in instrumentation, data analysis, and theoretical modeling. Conferences that once focused solely on galaxy formation and dark energy now featured entire sessions dedicated to multiverse research. Funding agencies responded by earmarking resources for interdisciplinary projects aimed at exploring the detection's ramifications. The event underscored the notion that some questions, those probing the deepest layers of existence, transcend national borders and demand a collective approach. In parallel, public institutions grappled with how to communicate the discovery responsibly. Outreach teams at space agencies and universities crafted materials that conveyed the significance without overstating the certainty. Infographics, interactive websites, and planetarium shows were developed to guide audiences through the evidence and the remaining open questions. Scientists participated in interviews, podcasts, and live stream events, offering transparent accounts of the data analysis process and the ongoing work to confirm the findings. The balance between wonder and scientific rigor became a central theme in public engagement efforts. The potential confirmation of another universe also spurred philosophical and theological reflection. If our cosmos were one among countless others, some asked whether this shifted the perspective on humanity's place in the grand scheme. The idea of multiple universes challenged anthropocentric views, suggesting that cosmic conditions conducive to life might be more rare, or more common, depending on the distribution of physical constants across the multiverse. Debates emerged within philosophical circles about the nature of existence, the meaning of probability in a landscape of universes, and the implications for notions of contingency and necessity. Meanwhile, theologians examined how the discovery intersected with spiritual narratives. Some embraced the findings as evidence of a creative process beyond human comprehension, viewing the multiverse as a manifestation of a boundless creative force. Others raised questions about the uniqueness of moral and spiritual experience in a context where parallel versions of ourselves might exist. The dialogue between theology and science deepened as scholars sought frameworks to integrate multiversal cosmology with age-old questions about purpose and existence. As the initial whirlwind of activity settled, researchers began charting the path forward. Key priorities included refining the data analysis to rule out residual uncertainties, designing targeted observational strategies to probe specific multiverse models, and developing the next generation of theoretical frameworks capable of encompassing the new evidence. Workshops were scheduled to draft a comprehensive multiverse roadmap, outlining critical experiments, necessary technological advances, and theoretical milestones. The goal: to transform the tantalizing hint captured by Webb into a robust scientific paradigm. The excitement also fueled educational initiatives aimed at nurturing the next generation of cosmologists. Universities introduced courses on multiverse theory, bubble collisions, and higher-dimensional physics, blending traditional lectures with hands-on data analysis of Webb signals. Scholarships and fellowships were established to support students pursuing research at the intersection of observational cosmology and fundamental theory. By embedding the multiverse within academic curricula, institutions aimed to ensure a pipeline of talent ready to tackle the profound questions raised by Webb's discovery. In the background of all these efforts lay the recognition of Webb's transformative power. Launched to probe the earliest epochs of cosmic history, it had already revolutionized our understanding of galaxy formation, exoplanet atmospheres, and stellar evolution. Now, it had pushed the envelope even further, venturing into territory once thought forever beyond observational reach. The detection of another universe stood as a testament to human ingenuity and the relentless pursuit of knowledge, a reminder that with each technological leap, the horizon of the unknown recedes, revealing ever more astonishing vistas. Yet for all the technical marvels and scholarly debates, the discovery retained a profoundly human dimension. At observatories and data centers, researchers shared moments of exhilaration as preliminary results coalesced into a coherent picture. Late-night conversations over coffee turned into animated exchanges of ideas, while distant colleagues connected through video calls to celebrate each incremental advance. The shared sense of wonder forged new bonds across disciplines and continents, reinforcing the conviction that some mysteries, especially those touching the very fabric of reality, belong to all of humanity. The quest to understand Webb's signal would likely span decades. Confirming the multiverse would require not only further observational evidence but also breakthroughs in fundamental physics capable of integrating the phenomenon into a unified framework. Questions about the nature of higher dimensional space, the mechanisms of bubble formation, and the interactions between universes would drive research at the frontier of cosmology, quantum gravity, and string theory. The journey promised to be long and challenging, yet imbued with the thrill of exploring the ultimate questions: why does anything exist at all? And what lies beyond the limits of our cosmic horizon? Beyond the initial ripples of discovery, a quieter but equally profound transformation began to take shape within the halls of theoretical physics. Scholars immersed themselves in the task of reconciling the newfound evidence of an adjacent universe with the frameworks of quantum field theory and general relativity. Traditional approaches to unification, seeking a single elegant set of equations to describe both the very large and the very small, now face the added challenge of embedding multiple causally disconnected realms. This spurred a renaissance of research on higher dimensional manifolds, where each universe emerges as a localized brane. Within an overarching multidimensional bulk, teams revisited long-neglected corners of string theory, investigating novel compactification schemes that might naturally give rise to bubble-like universes. In parallel, fresh proposals emerged for modifications to the Einstein field equations, so-called biometric theories, that could accommodate interactions at the boundaries between universes, all in pursuit of a coherent mathematical description of a multiverse. Meanwhile, the computational demands of analyzing Webb signals spurred innovation in data processing. Existing pipelines designed to handle terabytes of imagery and spectroscopy from deep field observations were retooled to capture even the faintest anomalies. Machine learning algorithms originally developed for exoplanet transit detection were retrained to recognize the subtle statistical fingerprints of interuniversal interactions. These neural networks sifted through mountains of archival data, re-examining every infrared survey in search of overlooked signatures. In some instances, algorithms flagged dubious candidates, phantom emissions at the margins of detectability that human analysts had dismissed as noise. Now, empowered by the context of a possible multiverse, those marginal signals gained new significance, prompting further targeted observations. The synergy between human intuition and artificial intelligence accelerated the pace of discovery, illustrating how advancements in computational astrophysics can open windows onto the most speculative domains of cosmology. At the same time, the scientific community confronted the logistical and ethical considerations of ventures into uncharted cosmic territory. Proposals circulated for ambitious space missions not only to extend Webb's reach but to deploy interferometric arrays at the Sun-Earth Lagrange points. These flotillas of small satellites, working in concert, could synthesize apertures hundreds of kilometers across, achieving resolution orders of magnitude finer than any single telescope. Plans for mission concepts dubbed Multiverse Mapper and Horizon Probe outlined instrument suites tailored to detect polarization patterns, spectral distortions, and minute gravitational perturbations. Yet with each design review emerged questions about resource allocation. Was it justifiable to channel scarce funds into missions whose primary goal was to confirm the existence of realms forever beyond direct interaction? Funding agencies grappled with balancing the allure of a paradigm-shifting discovery against pressing priorities in Earth observation, planetary defense, and exoplanet characterization. Public policy debates mirrored these tensions. Legislators and science advisors convened to draft white papers exploring the societal implications of a confirmed multiverse. Some argued that the transformative nature of the discovery warranted an immediate boost to space science budgets, arguing that humanity's long-term prosperity depends on pushing the boundaries of knowledge. Others cautioned against the spectacle science trap, oversubscribing funds to exotic endeavors at the expense of research with more tangible benefits. Interagency working groups emerged, bringing together representatives from space agencies, funding councils, and academic consortia to establish criteria for mission approval. These criteria emphasized rigorous risk assessment, peer review, transparency, and international cooperation, setting a precedent for collaborative decision-making in the pursuit of cosmic frontiers. In parallel with these institutional developments, a vibrant ecosystem of citizen science platforms sprang up. Inspired by the success of projects like Galaxy Zoo and Backyard Worlds, enthusiasts from around the globe signed up to comb through real web data. User-friendly web interfaces allowed volunteers to annotate images, flag irregular artifacts, and vote on whether candidate signals merited deeper analysis. A point system, gamified to reward diligence and accuracy, encouraged participation from hobbyists, students, and retirees alike. Not only did this democratize the scientific process, but it also generated a trove of human-curated insights that supplemented algorithmic classifications. For many participants, the possibility of contributing to the first confirmed evidence of another universe was a once-in-a-lifetime opportunity, one that bridged the gap between professional researchers and the broader public. As the years unfolded, interdisciplinary conferences on multiverse studies became fixtures on the academic calendar. Sessions ranged from the highly technical, detailing the renormalization group flows in a landscape of coupling constants, to the deeply philosophical, pondering the nature of consciousness in a cosmos with infinite variations. Art installations found their way into conference venues, translating complex data into immersive experiences. One exhibit projected live visualizations of simulated bubble collisions onto dome ceilings, accompanied by an ambient soundscape derived from mathematical mappings of the signal's Fourier transforms. Attendees described a sense of standing at the threshold between worlds, a visceral reminder of the profound shift in humanity's cosmic perspective. Parallel to these academic and cultural expressions, speculative fiction authors seized upon the discovery as fertile ground for new narratives. Novels, short stories, and graphic novels proliferated, each exploring a different facet of interuniversal possibility. Some authors imagined benevolent exchanges of art, knowledge, and music across the cosmic divide. Others wrote cautionary tales of technological contagion, what might happen if a rogue civilization attempted to bridge universes and unleashed unknown pathogens or destabilizing physics. These works not only entertained but informed public discourse, raising awareness of the potential risks and rewards inherent in multiversal exploration. Libraries reported a surge in demand for titles on cosmology and theoretical physics, as curious readers sought to understand the science behind the fiction. The economic implications also came under scrutiny. Could industries emerge around technologies inspired by interuniversal research? Companies ventured into developing more sensitive cryogenic detectors, ultra-stable lasers, and quantum sensors, spin-offs from instrumentation designed to capture cross-universe signals. These advances found applications in fields as diverse as medical imaging, navigation, and material science. Investors, sensing an emerging market, funded startups touting multiversal tech as a buzzword shorthand for next-generation precision measurement tools. In this way, the search for other universes catalyzed innovation far beyond the realm of pure astrophysics. Yet with opportunity came responsibility. International bodies examined frameworks for preserving cosmic heritage and preventing contamination. Just as planetary protection guidelines govern probes to Mars and Europa, scholars now considered principles for interuniversal protection. Although the prospect of physically traveling to another universe remained firmly in the realm of speculation, the notion of influencing or altering physics beyond our bubble, however indirectly, raised ethical questions. Debates emerged over whether humanity should actively attempt communication or instead adopt a posture of passive observation. These discussions paralleled long-standing conversations in the search for extraterrestrial intelligence, reframed in the context of universes rather than planets. Meanwhile, the philosophical reverberations continued to deepen. Schools of thought that once stood at odds, scientific realists, instrumentalists, and radical empiricists, found common ground in grappling with data that sat at the margins of empirical validation. Some pragmatists argued that the definition of observable universe must expand to include signals inferred through gravitational and spectral analysis, while others countered that without direct causal linkage, claims of another universe risked venturing into metaphysics rather than physics. These debates enlivened courses in the philosophy of science, prompting revised syllabi that treated multiverse cosmology as a case study in theory confirmation and the demarcation problem. Theological and metaphysical traditions also continued to absorb the implications of a potentially infinite ensemble of universes. Some spiritual leaders proposed interpretations in which each bubble universe reflected a different facet of a transcendent reality, an ultimate source that transcended the multiverse itself. Interfaith dialogues explored parallels between cosmological plurality and doctrines of multiplicity found in ancient texts. Conferences on science and religion featured panels where cosmologists and theologians spoke in unison about wonder and humility in the face of boundless creation. These conversations underscored a shared human quest for meaning that extended beyond empirical boundaries. Educational systems worldwide integrated multiverse concepts into their curricula at all levels. Elementary school lesson plans used simple analogies, bubbles in a foam bath, sheets of paper representing spatial slices, to introduce the idea of separate universes. High school physics courses offered modules on inflationary epochs and quantum vacuum fluctuations, while undergraduate programs launched specialized tracks in cosmology and high-dimensional geometry. Textbook publishers revised chapters to include the latest observational constraints, weaving the narrative of Webb's detection into the broader storyline of scientific progress. By embedding the multiverse into formal education, societies aimed to cultivate citizens equipped to navigate a reality more complex than previously imagined. The pace of discovery accelerated when researchers began exploiting synergies between different observational platforms. Data from neutrino observatories, sensitive to ghostly particles traversing immense distances, was cross-correlated with gravitational wave records from ground-based detectors. Although these data sets operated on vastly different scales, analysts searched for coincident anomalies that might betray an exotic event at the nexus of universes. A tantalizing hint emerged when a cluster of high-energy neutrinos detected over a span of weeks lined up with a subtle gravitational wave perturbation recorded days earlier. While the statistical significance remained marginal, the possibility of convergent evidence tantalized teams around the globe, spurring proposals for integrated multi-messenger campaigns specifically targeting interuniversal phenomena. In the policy arena, discussions moved toward establishing an international treaty for multiverse research. Advocates argued that, as with nuclear nonproliferation and space law, the exploration of realities beyond our own demanded a cooperative framework. Such a treaty would govern data sharing, instrument deployment, and hypothetical communication attempts, ensuring that no single nation monopolized access to the deepest cosmic secrets. Drafts circulated among diplomatic channels, drawing on precedents from the Outer Space Treaty and the Antarctic Treaty System. Although negotiations were at an early stage, the very notion of drafting such an agreement testified to the magnitude of what lay before humanity, the recognition that we stood at the threshold of a new era of cosmic stewardship. As momentum built for these grand initiatives, individual researchers continued to pursue specialized lines of inquiry. Some focused on the thermodynamic implications of bubble universes, exploring whether entropy gradients across the boundary might drive unidirectional heat flows or stabilize the interface. Others investigated the role of dark energy in mediating interactions between universes, hypothesizing that variations in vacuum energy densities could leave imprints on the large-scale structure of our cosmos. A handful of maverick theorists even proposed laboratory analogs, tabletop experiments in condensed matter systems designed to mimic interfacial physics, to gain intuition about multiversal dynamics. Though far removed from the cosmic scale, these analogs offered valuable insights into the fundamental principles governing boundary phenomena. In the realm of outreach and public engagement, virtual reality experiences matured into fully immersive journeys through hypothetical multiverse landscapes. Users donned headsets and traveled along inflationary bubbles, witnessing simulated collision events and navigating corridors of warped spacetime. These experiences, grounded in cutting-edge simulations, allowed people to confront the scale and strangeness of the multiverse in visceral ways. Museums and science centers deployed VR pods where visitors could explore alternate universes, each rendered with slightly different physical laws, from worlds where gravity was weaker to realms where atomic bonds formed distinct chemical pathways. By translating abstract theory into tangible exploration, these installations democratized access to one of humanity's most profound frontiers. The ongoing quest to understand Webb's signal and what it might reveal about other universes charted a course defined by patience, collaboration, and humility. While the initial detection had captivated the world, it represented only the first step in a journey that would span generations. The scientific endeavor transformed as researchers confronted unprecedented questions. How do we test theories when direct interaction is impossible? Can we develop instruments sensitive enough to listen across universes? What ethical principles should guide us in exploring realms forever beyond our causal reach? These questions, at once technical and philosophical, underscored the inseparability of empirical investigation and reflective deliberation. As the decades passed, the contours of multiverse cosmology crystallized into a mature discipline. Specialized journals appeared, dedicated conferences attracted thousands of delegates, and academic departments established centers focused on interuniversal studies. Yet even as the field professionalized, it retained the sense of wonder that had characterized its inception. Graduate students, seeing their predecessors' breakthroughs as historical fact, continue to ask bold questions. Could intelligent life in another universe ever detect our signals? Would there be a universal mathematical language transcending individual bubbles? And perhaps most hauntingly, what lay beyond the multiverse itself? In the end, the story that began when Webb's instruments first registered that faint, inexplicable glow evolved into a testament to humanity's enduring curiosity. It illustrated how a single observation, seemingly beyond the grasp of contemporary science, could reshape disciplines, inspire artists, and alter our collective self-conception. Although the path forward remained strewn with challenges, from technological hurdles to philosophical conundrums, the pursuit itself became a unifying force. Generation after generation of scholars, engineers, artists, and dreamers would carry forward the torch ignited by that moment when the veil between universes first flickered, reminding us that every discovery expands not only our knowledge but the very boundaries of possibility. If you like this video, please give it a like and subscribe to our channel. Also leave your comments below and tell us what are your thoughts on James Webb detecting another universe. We want to hear from you. Thank you for watching and see you next time.